Okay, hello and welcome back to CS492A, Unconventional Computing at KAIST in fall 2024. We've already started with chapter 1 about conventional computing. And you had this homework assignment to think about whether your PC, notebook, laptop, or whatever, Macintosh, Linux, Windows, whether this is a case, instance of a Turing machine, or whether it's an instance of a finite automaton, finite state machine. And we're going to now start again with chapter 1 and make a break when we arrive at this question. And then I want to discuss this together with you. And yeah, disclaimer, there's no wrong answer, but you need to be able to justify your answer, okay? So that being said, let's start the slides. Right, so here's the slide screen. Conventional computing. We've discussed, and I will recall, the difference between digital and analog signals and the benefits, explaining why contemporary computing is most dominantly digital computing currently. And then we will recall digital models of computing, including the two I just mentioned, Turing machine and finite state machine. We'll discuss examples and then talk about various ways that such digital modes of computing have been realized historically in the past and currently, mechanically, electrically, and currently electronically, but also possibly using water or using light. This is the area of fluidics and of soliton computing. Optical computing, and that leads us to discuss the Church-Turing hypothesis. The hypothesis that about the relation between physical computing devices and their computing capabilities. So let's recall the difference between digital and analog is their stability or instability under noise. In an analog signal, under noise, one tries to recover the original signal, but there will be an error. Whereas in a digital signal, if the noise is not too large, then it's still possible to distinguish between 0 and 1, between, let's say, 0 volt and 5 volt in old TTL logic, or between 0 and 3 volt in CMOS logic, depending on how these zeros and ones are implemented and realized in various physical ways. And the digital models of computing that we discussed capture the hierarchy, the abstraction hierarchy, climbing from a transistor up to high-level programming languages. And these models include Boolean gates, Boolean circuits, with and without memory, arithmetic circuits with and without memory, finite state machines, and Turing machines, which are equivalent to while programs, also known as FLOOP programs, but not as powerful, but more powerful than BLOOP programs. BLOOP programs have bounded loops, FLOOP programs and while programs have unbounded loops. And then there are high-level programming languages. So we talked about common ways of realizing Boolean gates. Here are typical types of Boolean gates with two inputs, one input or two input. If we want to process Boolean signals with more than two input, we need to somehow break down these, let's say, n inputs into pairs of inputs, n-ary gates into binary gates, and then combine these binary gates, for example, to realize a so-called full adder or half adder, which is one stage of adding n-bit numbers. This one adds two bits, and if we want to add n bits, we can do that by repeatedly adding 2 bits, but following the carry, and the next stage, input that output of the carry to the next stage, and thus we can iterate this. This is a directed acyclic graph. The edges here are implicitly directed from left to right. This is the way the signal is progressing. And there are no cycles, right? There are no loops here. Otherwise, there's a possibility of a possible inconsistency. On the other hand, with loops, we can store a bit. We discussed this. This is an example of a static memory bit, storing 1 bit of memory. And when the enable signal is triggered, then this 1 bit storage will change its stored value either to 1 if the set signal is on, or to 0 if the reset signal is on. When the enable signal is absent, then whatever happens with set or reset does not affect the state and the value of the bit stored in this 1-bit memory. And I mentioned and want to say it again, this is a pretty complex way of storing 1 bit, right? It requires 4 gates, and each gate typically in turn is combined from at least 2 transistors. So that's like 8 transistors with, oh, there's also negators here, right? So that's roughly 10 transistors in order to store 1 bit statically. And that's a benefit. When there's no enable signal coming, then it will store the bit indefinitely as long as the power supply is running. But more efficient ways used in current computers are dynamic memory, which use only 1 capacitor, but they need to be refreshed. And they need much less space. And therefore, this is the current state of the art of storing data dynamically. Anyway, so when we start discussing about unconventional modes of computing, our first goal will be to implement these Boolean gates, because once we have implemented these Boolean gates, actually one of them, a NOR gate or a NAND gate, suffices to implement the others. For example, by combining 2 NAND gates, one can recover the negation, or the AND gate or the OR gate. AND gate and OR gate alone are not sufficient because they are monotonic. Whenever one signal in the input changes from 0 to 1, then the output signal will never change from 1 to 0. It could be stay the same, or it could change from 0 to 1. That's monotonic. So in order to realize non-monotonic circuits, we need at least one non-monotonic basic gate, and the NAND gate will do, or the NOR gate will do. And we will try to implement these in unconventional models of computing and then combine them to thus recreate any more complex Boolean circuits with memory, and thus eventually also Turing machine. Speaking of Turing machine, your question, right, your homework assignment was to think about whether your computer is a Turing machine or finite state machine. Finite state machines are discussed in CS322. Turing machines, white programs, loop programs are discussed in CS422 by yours truly, and high-level programming languages are subject of CS320. But here's an example of a finite state machine for adding 2 bits. sequences of pairs of bits, right, with carry. And it has 4 states, 1, 2, 3, 4, depending on the one hand whether it currently has a carry stored or not. But that would only require 2 states, but here there are 4 states, and these are the transitions. So for example, if it has stored carry, but has not output a carry, and then it reads 0, 0, then it will output that carry and will have stored no carry. And if then it reads 1, 1, then it will not output, then it will output a carry and output 1 and store that it has stored a carry. So that's a 4-state finite automaton, 4 states, that's finite, right? And the general picture is that it has a finite number of states. It reads the input symbol by symbol. Here symbols are pairs of bits, and produces output. Here the output is 1 bit, the next output bit for this transition. Okay. The important thing is it has no memory except for the states. So each state represents one possible piece of information, but it has a finite number of states and therefore finite memory. A Turing machine, on the other hand, also has finite control with finitely many states. It reads one symbol from the tape. Again, that could be, for example, a pair of bits. And then, depending on what it has read and depending on its state, it not just outputs, but it can also change the content of the tape, and depending on the state and what it has read, it moves the head left or right or keep it at the current position. So that's a Turing machine. And the main difference is that a Turing machine has this tape for additional memory, and the tape is unbounded. It's a subtle thing. It's not necessarily infinite, but it is unbounded. So whenever the Turing machine goes right and exceeds, so it's bounded to the left, it starts here. And whenever the machine goes right and it encounters a new cell, then this cell is implicitly considered to be initialized with a blank symbol, for example. And so the question for you was, if you use this, look at this, such a notebook computer, is this a Turing machine or is it a finite automaton? How much memory, that's basically the question, does it have? And this is where I briefly stop here, and right. So now you can unmute yourself and discuss together. What do you think is your computer? Is it a Turing machine or finite state machine, and why? So for the record, let me repeat your answers. And you pointed out that indeed a PC can reasonably be considered as an example of a finite state machine, although the number of finite states would be ludicrously large, more states than there are electrons in the universe. So it is maybe more reasonable to consider a computer as a case of a Turing machine, but a Turing machine technically is supposed to have unbounded memory, whereas your computer, even one with 32 gigabytes memory, still has bounded memory, 32 gigabytes. So whenever your computer runs out of memory, that's where its behavior differs from a behavior of a Turing machine, which would not run out of memory. And that's why computers have virtual memory, because when a computer runs out of physical memory, then using virtual memory, it can access much larger amount of memory than is present physically in RAM. But even with virtual memory, 2 to the 64 bytes, so 32 gigabyte, that's 2 to the 35 bytes, 2 to the 64 bytes for virtual memory. Even that is still finite, is still bounded, and technically differs from the behavior of a Turing machine, although in practice that bound will never be experienced because 2 to the 64 bytes, that's more than everyone can even afford to attach to a computer. So thank you very much for this online discussion. And now we're going to start talking about physical computing, namely the question, how can one realize Boolean gates and then combine them to Boolean circuits with or without memory, historically and also maybe not so historically known. So the way we currently realize Boolean gates and circuits is using semiconductors, transistors combined into such integrated circuits as you see here. This is one from the Soviet Union, but the same technology was used in the United States and in the rest of the world. And this is just so nice because one can open it up and see what's inside. So this one has like 14 pins, right? 7 to the left, 7 to the right. 2 of them are for power supply. And inside, looking with a microscope, this is what's inside. And yeah, so these are several transistors here inside. And these integrated circuits are then combined into larger circuits, such as these boards. These are huge boards, heavy, and yeah, this is the history of digital computing, more precisely, electronic digital computing. And with electronic, I mean that the voltages used here are roughly in the range of 5 volt, sometimes 12 volts. But historically, before that, people first tried to build Boolean gates and Boolean circuits using mechanical devices. So here's a rebuild of a Boolean AND gate as used in the first SUSE computer, SUSE computer 1, used mechanical device means to build Boolean gates. And here you see a rebuild of this AND gate. So you see the two blue inputs, left and right. And then there's a clock signal which moves the yellow gates down. And if both blue bars have been pushed, then it moves down, and otherwise it doesn't. So can you see that animation? Yes, this is from Electric Trickery website animation. And here's a similar way of implementing an OR gate. The difference is what happens inside. This is covered. Okay. And here's another gate, which is kind of for you to guess what kind of gate is that. Anyway, that's your next homework assignment. I'll upload the slides, and by the way, also the lecture is recorded and uploaded in YouTube. So you want to review it and find out what kind of gate is realized in this mechanical way. And as I said, yeah, this is how, by combining such gates, complex Boolean circuits can be realized. And this is exactly how Konrad Zuse built his first computer, the Z1 computer, which was destroyed during the Second World War. He built it from 1935 to 1937. What you see here is a replica in a museum using modern mechanical devices, because one problem that Zuse immediately ran into is that these mechanical devices tend to get stuck. So he never managed to have his computer run for more than a few minutes before, simply because there are so many gates, right? That's the thing. The principle of computing is to use very basic, few basic operations, like here, the Boolean gates, few very basic, and then combine them, thousands of them, millions of them, to realize more advanced functionality in your computer, even billions of them. But with billions of them operating, they have to operate really reliable, right? Because if only one of them fails, then maybe you run into a blue screen, right? And the probability for one of them to fail multiplies with 1 billion if you have 1 billion of them. Zuse had thousands or 10,000 of them, so that still was sufficiently high probability for some failure to after a few minutes. So his machine would weigh roughly 1 ton and would run at a clock frequency of roughly 1 hertz. That's his machine, Zuse Z1, but it was destroyed, and here's a replica. And that led Zuse to create his second machine, Z2, taking care of the reliability. So what is more reliable than mechanical gates? He switched from Boolean gates using these mechanical means to relays, which are electromechanical. So electromechanic computing, because the mechanical computing turned out to be too prone to faults. And here you see one of the relays that that Zuse used. Originally, these relays were used in telecommunications for the German telephone system, connecting phones from one home through city to another city, and in another city to another home. So these are control switches originally for relaying audio signals, switching audio signals, but Zuse used them for switching digital signals. And he bought used such relays, roughly 300 of them at a cheap price because they weren't used anymore, and then combined them to build his Zuse Z2 computer, which would weigh less, only 300 kilograms, and run fast at a clock frequency of roughly 10 hertz, and most importantly, more reliably. I mean, this works, you can imagine that this works reliably, and it had to work reliably because it had been used in the German telecommunication system for years, for decades. So pretty must have been reliable. But still, there were some errors sometimes, and this is where the famous name computer bug comes from. Not Turing, but in the United States, similar machines were built a little bit later. So here you see a report from a computer operator running such a computer, electromagnetic computer, which would cause a fault. It didn't run the program as expected. And when trying to find the cause of the fault, they found that a bug had been stuck somewhere in the electromechanical switches and prevented it from operating. And here you see the logbook says first actual case of a bug being found. So here the bug had been restored, preserved, and this is why computer errors are in our case nowadays called computer bugs in reference to this bug. So they were still faulty. The reliability was larger than with purely mechanical, but also electromechanic computers had reliability issues that prevented them from scaling up to beyond thousands. The aim was maybe for 10,000s of the relays, but this was not reliable enough for 10,000s to work reliable over a long run of time. And this is what led Konrad Zuse and others to switch to abandon all this mechanic and electromechanical computing and instead switch to purely electric computing with no moving parts, no mechanically moving parts. And what electric switches use? These are these cathode tubes, okay? So you see these, they are based on electrons moving in vacuum. So these bulbs had to be evacuated, all air had to be removed, most of the air, and then one could control the flow of current from one pair of inputs to another, controlled switch again, and then combine hundreds or thousands of them more reliably. Still, sometimes some of these bulbs would fail. Maybe the air would enter it and then they stopped working. But still, again, much more reliably than electromechanic, which in turn is much more reliable than mechanical. And here you see a picture from the famous Colossus computer, which was built and run in the United Kingdom. Actually, many of these Colossus computers were built, and you see sequences of these bulbs here, right? Triodes, technically, seen from the top. And here you see, yeah, this is the Colossus series, built at United K, 1943 to 1945. This is the Second World War time, the time where the Second World War was decided. And this Colossus series was used to break the code of the German military in the United States. You might have seen the movie about Alan Turing, who was also very influential in breaking the German military's secret code so that United Kingdom, England, basically was aware where Germany would strike next in London, for example. And they were faced with a dilemma, right? So they could decipher the German secret messages where Germany told their pilots where to fly and where to drop the bombs. But if England was in the position to start intercepting planes of their own, right, to prevent the German planes or evacuate that part of the city. But if that happened too often, then Germany would have become suspicious, right? If each time German pilots encountered a deserted city or were faced each time with defensive measures, then Germany would have become suspicious. So England was very smart and but also in this ethical dilemma and only exercised countermeasures sometimes, so that Germany never got suspicious that they actually had been hacked all the time. And was due to the Colossus series. More than 10 of these computers were built. Here you see one of them. And now I want to ask you, have you heard of the Colossus computers? You may have heard of the Enigma computer, right? This is which is featured in the Turing movie, right? But this is not Enigma, this is Colossus. Who has heard of the Colossus computer? Please raise your virtual hand if you have heard of Colossus computer before. You have not, right? Exactly. And there's a reason for that. Because after the war, after Germany had lost the war and England had won and United States and Russia together had won the war, all instances of the Colossus computers were dismantled into so small pieces that was impossible to recover the original. This was for intelligence reason, to prevent them this crucial military advantage information from leaking. And also all plans for building these computers were burned. And that's why nowadays only very few people remember these computers, and they regret having destroyed everything and having burnt anything. And now I want to take a short break and show you a movie, a video there about where people remember this advanced technology, electric computing. And by the way, what's the difference between electric and electronic? Major difference is the amount of current used. So in electric computing, remember, we're talking about 0 to 5 volts, sometimes up to 12 volts, and we try to minimize the current. Electric computing, which is different from electronic computing, in order to run these tubes, requires heating them and providing high voltage for the electrons to pass through the vacuum of plus minus 200 volts. So this is electric computing as opposed to electronic computing. And now I'm gonna interrupt sharing the slides and switch to this video about the Colossus computer. Okay.
Welcome to another video from explainingcomputers.com.
Right. So this is a little first promotion advertisement for the Computer Museum in United Kingdom. And now we're going to look at other ways of realizing Boolean gates and Boolean circuits beyond mechanical, electromechanical, electric, and electronic, or ways we have seen so far, namely using fluids. So this is the area of fluidics, which is not much different from what we have seen so far because it's still based on Boolean gates combined into Boolean circuits based on these control switches only that the control switches are now not electronic like transistors, or mechanical or electromechanical like with these relays, or electric like with the tubes, but instead using liquids or gases. Fluids means liquids and or gases. Now here's an example of a controlled switch, which is simply a valve, right? Solenoid valve, where the flow of the liquid, water or gas, passes through this gate, and the gate can be opened or closed with this device, which is secured with a spring, and either with electronic or with electric or with pneumatic. This gate can be opened or closed. But this is not fluidic, because it still has moving mechanical hard parts, this part, right? So in fluidics, we prohibited moving hard parts. Only the fluid, liquids or gases may move. So this is not about fluidics. Fluidics was arguably introduced or started by genius, namely by Tesla, right? You may know Tesla from the cars, right? But it's actually named after Nicholas Tesla, the famous Serbian, base we would say maybe Hungarian inventor. And he invented a fluid counterpart to a diode. You may know a diode is where the current can go in one direction, but not in the other direction. It's a one-directional electronic gate. And here's the so-called Tesla valve, which does the same. So if the fluid comes from here, from the right, then it can simply pass through here, and all these side lines don't really matter, and it passes through and leaves here. So that's actually a picture from his patent. So in this direction, the valve is open. In the other direction, fluid cannot pass. Why not? Because it gets sidetracked here. Part of the fluid gets sidetracked here, and the other part passes through here. And here the two parts merge again, causing a lot of turbulence. And then the same happens again. Part goes here, part goes here, and here they both meet again, creating turbulence again, and here creating turbulence, and here and here. And all these turbulences effectively prevent fluid from going from here to here. And the interesting thing is, the higher the pressure, the more turbulence and the less leaves here. So it is possible for fluid to go from here to here, but only very slowly, and only when there's no pressure. Then it can gradually drip through all this. But with high pressure, it produces a high counter pressure, preventing, so only in one direction, but not in the other. So in this example, there are 1, 2, 3, 4, 5, 6, 12 of these turbulence creating devices. Can have more or less, but this is a very interesting basic principle. And observe that indeed it has no moving parts. Only the liquid moves in these funnels, along these gates. There is surrounding material, right? But the surrounding material hard part is fixed, and only the fluids move. This is the famous Tesla valve. And here you see another illustration, schematic illustration. The low one is from his patent application, and the upper one is from Wikipedia. The lower one shows how the fluid moves, and the upper one shows that the fluid creates friction with itself. The black and the red parts create friction with itself. And this was maybe the start of fluidics. And then one can build maybe more complex Boolean gates from these. And here you see such a Boolean gate. Actually, it's two Boolean gates in one. Here enters one stream of fluid, like water. And here, that's A, and B, another one enters. And they meet here, and their horizontal forces cancel, so that only the vertical impact continues, and they end up in this cup, where it is then removed into in the Z direction, which is not shown here in this two-dimensional plane. So this is a three-dimensional device, a three-dimensional AND gate. There's also an XOR gate in the same, namely when only fluid enters from gate 1, but not from gate 2, then it eventually hits the wall of this yellow region, white region. Black is the surrounding material, and it exits here to the bottom. Same when only water enters in B, but not in A. But when both enter, then they end up in this cup and don't get to leave through this XOR output. So that's an exclusive gate. And using both AND and exclusive OR, one can again combine any other Boolean circuit by combining these. So again, observe no moving hard parts, only the liquids move, and in order to realize Boolean gates. So yeah, we're already running out of time. I'm showing you some more complex gates. So here you see negated AND, negated A, and multiplying system symbol means AND. And here you see an OR, A or B. So if A or B comes fluid in, then it leaves here. And anyway, you can figure it out. Here's yeah, we need amplifiers, right? So this supposes that the input streams come with some pressure, equal pressure, but they leave without pressure. So we need to repressurize the output before feeding it into the next gate. And these are devices how to recreate pressure, a control switch. So this is a power stream which always puts in pressure. This is like the electric power supply that also your electric gates use, right? They need some power supply for the control switch. Here's the control jet. The control jet doesn't need much power, and it determines whether the power stream leaves here or here. And when the power stream leaves, it has power again. So this is a way of amplifying the control jet from here or from here. So even with a weak control jet, one can recover its signal, but now leaving with high pressure given by the power stream. So yeah, I think we're out of time. Next time, I'm going to show you a video of an actual liquid computer, and then we're going to discuss other ways of using water in order to realize Boolean gates. And thus this is still conventional computing because it's digital and it's Boolean gate, but it's now using not electric, not mechanical, not electromechanical, and not electronic, but instead liquids for realizing Boolean gates. So yeah, that's all for today. Stop sharing. And yeah, I wish you very happy and all the best for Chuseok. And we'll meet again next Thursday to continue talking about water computers.